Good morning.
Morning.
For attendance, let's review this question. It's one of those examples for logarithm differentiation. The function has variable in the base and variable in the exponent. So we have to take the logarithm of the function and differentiate both sides of the equation. So we're going to use implicit differentiation to help us to try to do it. So we try to change the form of the function so that it's not a exponent. We want to convert it to a multiplication. So after the change, logarithm of the y value is now equal to, this is a logarithm, but we have power in the logarithm function. According to the law of logarithm, the exponent inside the input can be moved to the front. So we move the logarithm to the front. But even if after you move the logarithm to the front, you still have logarithm of x. So it actually becomes this. Okay, so what we're going to do is, this is actually ln of x times ln of x. So now we have ln of y equal to ln of x squared. And then we will differentiate both sides of the equation. If we differentiate the left side, what do we have?
Y prime over y.
Y prime over y. Because y is a function, so we have y prime over y. Now, what do we have on the left side? Assuming that x is the independent variable, and realize that what kind of variable really affects how you do the calculation. What do we have? The outside is the power of 2, so using the power rule is
2 ln x.
2 ln x. That's because the power of 2. But then we have, it's not x to the power 2, it's ln to the power 2. So we still have to differentiate the logarithm of x. So what we have here is, you take care of that power 2. Now that after that's done, you can just forget about it, and then we differentiate what's left, which has derivative
1 over x.
1 over x. So that's what we have left, and then we can already see this is the finished differentiation. The rest is all algebra, because our goal is to try to find y prime, which represents the derivative. So we have to have y prime by itself. So what do we do?
Multiply by y.
So we multiply both sides with y, so then we have y prime equal to y times, guess we should organize this a little. So y times 2 ln of x over x. If you multiply the reciprocal, it's kind of like the division. Right? And then realize y was originally a function. We have definition for y. So we want the whole derivative to be in terms of x. So we're going to replace the y. The y in here, you're going to replace it with a function of x. So y prime is now equal to x to the power of logarithm of x, that was the y, times 2 ln of x over x. Okay, the way I write it is not the it's not identical to the choices. You have to work out the algebra. Remember, multiplication can switch order. A times B equal to B times A. With that, I think we can make a choice now, right? Switch the order of operation. So you can move the 2 to the front, because normally we write the coefficient 2 not in the middle of the multiplication, but at the beginning of the multiplication. If you have any division, then this division by x, you can write it as division of the whole multiplication instead of have it multiplication of the division. So rearrange the factors, and you should say it's one of those choices. I just want to use this question as a review for logarithm differentiation. Oh, we can also look at this. All right, so like I said, we try to rearrange the term. So for example, you would move the 2 to the front, remove the 2 to the front, and it looks like a 2 times the denominator x is in the denominator. If you have exponent, you want to write exponent last. And then the polynomial would be before the exponent. That would be x. So that would be the way I would write it if I was to write the. So the answer is C. Any homework questions? Are we doing okay with the chapter 3 assignment? Right now the chapters are the only one that are open. We're gonna have a test after the break. Next week is the spring break. So this is like the last day of this week's class, right? So next week's spring break. Any plans for the break?
Doing a volunteer trip down to Miami.
That's cool. All right. If there's no more question, I'll continue what we started in chapter 4. We already talked about related rates. I think we spent 2 days on related rates. I'm going to move a little bit forward. But still, any of the past homework, past material, if you see questions from the homework that seems to be giving you a hard time, we can also always work it out together in class. So feel free to bring up any past material, past question. But if nobody mentioned any question, we're probably going to bring up a new topic, new questions to discuss. So we're going to talk about section 2 today. Um, 4.2. I think it's a L'Hopital. The pronunciation is between a little single. That's I think it's French.
Yeah, that's right.
Yeah. The H is silent, so it's pronounced L'Hopital, even though it has the H in there. Sometimes I just call that LH rule because I really couldn't remember the pronunciation or the spelling. Occasionally, I even have a little X because I would say the hospital, the word hospital, but it's not. Anyway, it's a special rule. I assume this one would be slightly more formalized way of solving limit calculation. It's different from section 1. Section 1 is all word problem. In my mind, word problem, it depends on all your past experience a lot more than this. So this, you can think of this as brand new. So you can learn it from the beginning and practice the same type of question over and over. For the related rate question, it's really read a word. If it's a scenario like if you are in finance or if you're in a economic class, you're more familiar with that type of question. If you just finished your geometry, you're more familiar with the geometry type of question. So it depends a lot on your background knowledge that's not included in this class. So that's what's hard about it. All right, so this L'Hopital rule is a special way to help us solve some of the difficult limit calculations. So we have to review what we talked about in chapter 1. We were talking about all kind of limit calculation, and the limit calculation, the difficulty depend on the type of question. So we did talk about a different type of limit calculations. Let's review. So in chapter 1, we did talk about limit calculation. All right. If you see a limit calculation, like limit of the f of x, how do we calculate it? The first attack is try to see if substitution will work out. Substitution. So you substitute the limit value into the function. See, you're calculating limit of function f of x if x is approaching a. All right. So the first thing you do, you would start calculating. Let's plug in the a to the function f of x as f of a. So the first attack we have for limit calculations, we're going to plug in a number to see if that works out. But then if you calculate it, let's say this function has division, the a somehow ends up being the denominator, causes the denominator to 0, and division by 0 causes like, hey, I calculated f of a, I substitute, somehow it's undefined. So we'll have a problem if we just do simple substitution. Sometimes you see f of a and you put it into a calculator and nothing works out, means substitution will fail sometime. So if substitution failed and this f of a does not produce a valid answer, which basically means the function is not continuous. If f of a does not exist, if this is d and e, then we know something is wrong, and a value is causing the function to be undefined. And then if this is undefined, and we call this situation indeterminate. So that means you can determine the limit by simply substitute the x value. So what we're going to do is we're going to try to look at the reason why it's indeterminate. Here we're going to talk about a couple of different scenarios. Indeterminate form. One of the form, indeterminate form. Oh, that's the way how to spell it. Because indeterminate. Okay. Right, the first form of indeterminate case is you have a limit of a division. So let's say you have a limit p of x divided by q of x. And x is approaching number a. The first case is like p of a equal to 0. Q of a equal to 0. Okay, so first scenario is you plug in a function, and the function has a division and a fraction, and the numerator of the fraction equal to 0, denominator of fraction equal to 0. That's going to cause a problem if you calculate limit. But that doesn't really give a decision that this limit does not exist. No, that only tells us this limit cannot be determined by simple substitution. We're calling this kind of indeterminate case 0 divided by 0 case. All right, this is not the only type of indeterminate case. There are also other situations. For example, instead of division, you may have multiplication. So for example, you have limit of p of x multiplied by q of x. X is approaching a. All right, and then as a result, maybe p of a somehow equal to 0. But then the limit of q of a, the limit of q of a, q of x when x approach a equal to infinity. So that's the so-called 0 times infinity case. That's also indeterminate case because you see, if the limit equal to 0, if one of the factors equal to 0, we know 0 times anything equal to 0 except infinity. All right, so 0 times any number, then 0 times 5 equal to 0, 0 times 100 equal to 0, 0 times 1000 equal to 0, but 0 times infinity is not 0. So if we have 0 multiplied by this limit is infinity, this limit equal to 0, we call that indeterminate case. So we have to look into like this infinity compared to this limit, which one has a higher power, which one has a bigger impact on the overall multiplication. That's the thing about this is the thing about power. Sometimes we call that power. Sometimes we call that analysis of order, like which one has higher order. That's why sometimes in higher level math class we say this infinity compared to this infinity, they're not the same infinity. You want to look at which one have a higher order infinity, or this is 0 and this is 0. They both have limit 0, but which one has a smaller 0, like a higher order 0. So anyway, so that is what's causing us to figure out another way for the limit calculation. In the past, we don't have a systematic way of solving this kind of question. What's happening is for both of these, we're going to look for a factor among the two and try to cancel common factor. Hopefully, after canceling the common factor, it's no longer 0 divided by 0 scenario. So in the past, to deal with the indeterminate cases, what we're going to do is to try to find a way to cancel out the common factor and change it into a determinate case. Change it into like scenario number 1. We're going to change it to scenario number 2 to number 1. So we always try to figure a way to turn a complex question to a simpler question. There's always that conversion, that simplification that was going on. And this is the idea for almost most of the questions. You see a hard question, what you think, instead of giving up on the question, you think, can I change this to several small, easier questions? And then we're going to solve those easier questions one by one. In the end, we'll solve the entire question. So, or maybe we can figure out a way to simplify the hard question to a less complicated question. So we always try to find a way to get around things. Okay, so in the indeterminate case, we're going to look at the first scenario. Suppose the limit of the numerator equal to 0, limit of the denominator equal to 0. Then the whole limit is called 0 divided by 0 scenario. That doesn't mean there's no 0. That doesn't mean the limit equals 0 divided by 0. It just tells us we have to, other work must be done to evaluate the limit. Basically, it says we got to do something else to figure out the limit. And now, so I talked about 0 divided by 0. We have 0 divided by infinity. We also have 0 divided by infinity divided by infinity. There is also 0 infinity minus infinity. Which one is was the answer 0 or was the answer infinity? Really depend on which one is truly larger. So, like I said, infinity may be one infinity may be much larger than the other infinity. 0 to the 0 power, 1 to the infinity power, infinity to the 0 power. So there's a couple of scenarios for the one that we cannot decide. When I was in college, I was like multiple cases. So like, how do I decide which case is this? Do I have to memorize every single one of those methods? No, actually, the way you can think of this, we all fall into one of the category, either division 0 divided by 0 or infinity divided by infinity. It just means that they're comparable. So if it's division, they fall into the same category. If it's multiplication, this multiplication, or the multiplication, that's the second category. And 1, 2, 3, the other 3, they're all the exponent form. So if you think about mathematical operation, they're either summation, which summation is the only one you don't have to worry about. Infinity plus infinity is infinity, 0 plus 0 is still 0, so there's no doubt. So subtraction, multiplication, division, and exponent. That's pretty much all the possible form. So in the end, when you think of it, you can kind of group them into different categories, and it's less complicated when you think of it. And the method for For all three are similar. The method for these is also similar. We're going to start with the first one, which is division. Okay. L'Hopital rule, part 1, and then probably part 2. Okay, so what this case is the 0 divided by 0 case. So suppose numerator approaches limit 0, denominator approaches limit 0. So what we can do is we can simplify the limit calculation. So instead of calculating the limit of f of x divided by g of x, we can calculate the limit of f prime of x over g prime of x. So we convert from one limit calculation to an equivalent limit calculation if the numerator and denominator both have the 0 limit. I mean, if one of them is 5, the other one is 6, we don't want to do that, right? If this is 5, this is 6, it's 5 over 6. And right, there's no reason to do L'Hopital. So remember, L'Hopital is not a general rule to solve any limit calculation. It's a rule to solve the indeterminate scenario, which really is the one that takes more effort. Okay, so let's look at how does it help with some of the calculation we had in the past. We used to have a really hard time analyzing these. This one was okay. I think we can factor this. The number 4, we can factor this, but when it comes to 1, 2, this one I think you can, if I try harder, I can use complicated factor. But 1 and 3 are the one that normally I always think about L'Hopital. We did try to solve the number 1 using the squid theorem with a little bit of geometry here. You have look at unit circle and look at the ratio between sin x and x. That was the case in chapter 1. But then again, all of these can be solved by L'Hopital's rule. And the solution for this limit calculation using L'Hopital's rule is the same answer as we were getting from chapter 1. So let's try this. Here we're going to do it one by one. We're going to start with the first one. All right. Normally, if you're applying something, if it's possible, we try to think about what was that about, and then try to apply it one-to-one. So, for example, the L'Hopital rule part 1 says, suppose limit of f of x divided by g of x, x approach a number. Suppose it falls into 0 divided by 0 case, which means the numerator and denominator both approach 0. Then this limit is equal to limit of f prime of x divided by g of x, g prime of x. So we will find the derivative of the numerator and derivative of the denominator, and then we divide it. This is by no means a quotient rule. No connection with the quotient rule whatsoever. We're not finding derivative of f of x over g of x. We find f of x derivative alone and find derivative of g of x alone. So it's not the same thing. It has nothing to do with the quotient rule. It has something to do with how things change. As x approach a, f of x is changing, g of x is changing. So since we are both approaching 0, so we think the ratio between their changes is what we're concerned. So we will find the derivative just so we can compare the rate of change. Let's look at the first example. According to our rule, we're going to try to let limit x approach 0. And here we're going to change the entire fraction. We'll find the derivative numerator, which is cosine x. And we'll find the derivative denominator, which is 1. And then you see now, this limit calculation, if x approaches 0, we can now substitute cosine 0 equal to 1. It's really 1 over 1. And so now we know the answer is just 1 over 1, which is equal to 1. And that's a lot easier than what we had in the past. There's a squeeze there. Any question? Yes. The first example. Second. As you can see, one of the benefits of doing L'Hopital's rule is most of the time, if you see a power function, a polynomial function, after you differentiate it, it lowers the power, it lowers the order, and that's nice because you can get rid of the power. Sometimes end up having constant terms, and that's the same thing over here when we try to differentiate. we try to find the limit. So the second question, we're going to keep the limit, the midpoint. So we want to make sure x is approaching 1, and that should be identical from the original question. So now we're going to find the numerator derivative. What is the derivative of this?
Negative x plus 3 to the negative 1/2.
Negative 1/2. Well, what about the coefficient? This is x plus 3 to the power 1/2, right?
Yeah.
So according to the power rule, we have to move the 1/2 to the front, right?
Oh, yeah.
So it's 1/2. And then the power minus 1, which is negative 1/2.
Yeah.
And that makes it 1 over root of x plus 3.
Yeah.
So that's the derivative. And then the derivative of 2 is 0, so that's gone. Derivative 1 is 0, so this is really negative 1. That's what we have. Again, so you can see as we apply a lot more other rules, other things, and we still have to practice differentiation of the function. So what we did in chapter 2, like finding derivative of this and finding derivative of that, they're still being applied constantly with all these questions. All right, so we're going to make x equal to 1. You can see if x equal to 1, that's 1 plus 3, which is 4. Root of 4 is 2. So that's 1 over 2 times 2, right? So 1 over 2 times 2 is 1 over 4, and this is using a negative. So the answer is a negative 1 over 4. That's the entire process. Any questions? This calculation, what we were doing in chapter 1 is try to multiply the numerator by the counter. So you multiply this whole thing by root of x plus 3 plus 2. And you're going to multiply the same thing to the denominator. And that was the method that we were using in chapter 1. And after we distributed, the numerator will be x plus 3 minus 2, which ended up being x plus 1. X plus 3 minus 4. So it's actually x minus 1, right? So the x minus 1 will cancel the 1 minus x. So give us a negative 1 coefficient. And this part is what's causing negative 4. Okay, so that's the green notion was what we were doing in chapter 1, but the red one was what we have in chapter, this is already chapter 4. Moving on to question 3, we're running the same process. We're gonna try to find the derivative of the numerator. Now, what's the derivative of the numerator?
2x.
2x. And what's the derivative of the denominator?
Sin x.
Sin x. Now, if we make x equal to 0, what will happen?
Well, it's going to be 0 no matter what. Because
well, yeah, so numerator is 2 times 0, denominator is sine 0, they're both 0, right? So it's still going to be 0 divided by 0. So we can still do L'Hopital, right? As long as it's still 0 divided by 0.
So we do it again.
Yeah, we do it again because it's still satisfying the L'Hopital condition. According to the L'Hopital, as long as the numerator and denominator both approach 0, we can apply it. So we're going to apply, sometimes I just write LH, apply the L'Hopital, and we're going to apply L'Hopital one more time. Then you're changing your limit calculation again. The numerator will have a derivative of 2 of cosine x. Now if you make x equal to 0, what will happen?
It becomes 2.
So the value is 2. So that's our limit. Okay. So this is one of those scenarios. It will be pretty hard to do it without the L'Hopital. And that's why it pops up in this section instead of anything earlier. Last one, we're going to do power rule for the polynomial in the numerator and the denominator. So if we make x approach 2, and we're going to change the numerator and denominator. What was the derivative of the numerator?
2x plus 1.
Okay, so, and then denominator?
2x minus 3.
Okay, now can we substitute? What's the numerature? What's this? 5 over 1. So the overall limit is 5. Any questions? You can always double check if it's right. I mean, just make x equal to 2.1. And you go 2.1 squared plus 2.1 minus 6 over 2.1 squared minus 3 times 2.1 plus 2. You know, see, it's not going to be identical to 5, but it should be pretty close to 5. And that way it will confirm what we have. But sometimes if you finish the whole thing and then you plug in a closer number, and the value is very, very different from what you have there, we probably should be concerned, like what's going on, what was the problem there. So it is always beneficial to have multiple ways to handle the same question, so then they confirm each other. If they don't confirm each other, then you have to think about your method. So the more experience that we have, the more likely we can detect the problem. So just give us example for the L'Hopital of the first type. Okay, part 2. Now, remember that we have 0 divided by 0 case. We also have infinity divided by infinity case. So part 2 says, suppose when x approaches a, the numerator f of x is approaching infinity, the denominator g of x also approaching infinity. So that's infinity divided by infinity case. We are able to apply L'Hopital. The limit of this division is equal to the limit of these new divisions, where the numerator finds derivative, the denominator finds derivative. So basically, it says that the L'Hopital can be applied if the numerator both approach infinity. Kind of like the first scenario, part 1, we say we can apply L'Hopital if both numerator and denominator approach 0. The part 2 says we can apply L'Hopital if both numerator and denominator approach infinity. So either cases, we're looking at a comparable scenario. Part 1 is numerator and denominator, they're both getting really, really, really small. And the ratio, we're going to see what that ratio is pushing to. Part 2 is saying numerator and denominator, they're both getting really, really large. But this ratio still are going to be determined by relatively to each other or with a proportion. So again, L'Hopital applies to that scenario. The second one is saying, or in the second case, it's kind of the limit at infinity, right? This says when x goes to infinity, if the numerator and denominator both approach 0, or when x approaches infinity, both numerator and denominator approach infinity, then we can also apply L'Hopital. So the second part basically is saying, that one is a finite number, x approaching a finite number. Now here we're saying x approaching infinity, L'Hopital still apply. So this is just making the L'Hopital rule more general. We kind of confirm different cases. Case 1, 0 divided by 0. Case 2, infinity divided by infinity. This is when x approaches infinity, whichever case. So actually, after a little while, I mean, when I was in college, after a couple of semesters, what I think in L'Hopital is that whenever the numerator and denominator is 0 by 0 or infinite by infinity, I don't really remember this can be considered a separate case, but in the case of like this or this, both limit calculations to me. Okay, so let's look at these two scenarios. And we did have method for the first one, right? Behavior and infinity for a polynomial, it depends on the highest power, right? So, and then you look at the highest power is 3 over 4, so we know the limit is 3 over 4. That we actually have a much quicker way than doing L'Hopital. But here we're going to use L'Hopital to confirm that. The second one we really have no way, but this is one of the scenarios we're going to compare, which if x goes to infinity, then the denominator goes to infinity, numerator also goes to infinity, which one's bigger? Typically, we think numerator will be higher. So I think this limit is infinity because exponential growth, it is always faster than polynomial growth. So I think without calculation, but just by looking at the type of question, I know exponential function grows faster. So the limit must be infinity. So there are other ways to handle limit calculation, but L'Hopital can confirm what we what's our perception. Okay, so we're gonna save this. I will leave a record of what we did without watching the video. Alright, so let's look at these two questions. The first question, using L'Hopital, we know that the numerator and denominator both approach infinity if x goes to infinity, but we can do L'Hopital. If we apply L'Hopital, we're going to find derivative of the numerator, which is 6x minus 100. We'll find derivative of the denominator, which is 8x plus 5, right? But x goes to infinity, so 6 infinity is still infinity, 8 infinity is still infinity, so still infinity divided by infinity. So we're going to apply L'Hopital one more time, meaning that we're going to differentiate numerator and denominator separately. So differentiate the numerator, you get 6. Differentiate the denominator, you get 8. X goes to infinity. By now, it's constant number, so we know the limit is 6 over 8 or 3 over 4. And this really confirms what we are thinking. Like the highest degree is 3 over 4, and that's what the limit at infinity is. So that's the horizontal asymptote of the entire function. This one. Again, numerator approaching infinity, denominator approaching infinity. So apply L'Hopital, we will find the derivative of the numerator, which is
E of x.
e to the x. What is the derivative of the denominator?
3x.
It's 3x squared. Okay, so now x goes to infinity. This is 3 times infinity. This is e to the infinity, so it's still infinity, still a really, really large number. So we're going to find derivative of the numerator, which is e to the x. We're going to apply L'Hopital one more time. Over 6x. But if x is really, really large, say x equal to 1,000, the denominator will be 6,000, numerator will be e to 1,000, and e to 1,000 is a number that most calculators cannot handle. So you know, it's e to the 6,000, e to the 1,000 is a super large number. So, but other than that, let's apply L'Hopital. We know it's still infinity divided by infinity, so apply L'Hopital one more time. E to the x over 6 now. Now, e to a infinity number, e to a super large number is going to be a really large number, but the denominator is not finite. So you have a really, really large number divided by a finite number, so the whole division will be a really, really large number we call infinity. So when we say infinity, it's a hypothetically arbitrary large number, so we know the answer is infinity. And that confirms our perception that that's exponential growth. This is polynomial growth. Exponential growth is much, much faster than polynomial growth, so that division causes the final answer still a growth function. Since it's growing without bound, and that's what we call infinity. Any questions? Dealing with infinity is always a little bit abstract because we don't see the actual number. But if you want to confirm this, you can always make a few calculations to see the tendency. For example, you can make x equal to numerator and denominator x equal to 1,000, and then you make x equal to 10,000. You see the difference. E to the, well, I think it's a little hard to calculate. Let's just make x equal to 10, like e to the 10 over 10 to the power 3, and e to the 100 over 100 to the power 3. And you're going to see the number gets much larger each time you increase the x value, which shows the tendency of growing without bound. Okay, so this is the example. Any question? All right. Let's move on to more cases. All right. So other cases. We talked about division, which is a factor form. So we're going to move on to the multiplication or subtraction form. Form number 1, 0 times infinity, which is on the 1 and 2, example 1 and 2. You see, x times e to the 1 over x. X is approaching 0. 1 over x is approaching infinity. So this is really e to the infinity, and that's what's making it really large. So the e to the 1 over x is really large, x is really small. Suppose x is approaching 0. This is approaching 0 from the positive side. So x is equal to 0.2, 0.1, 0.11, but it's never negative. Positive is guaranteed when it's positive. Number 2, the same thing if x is approaching 0 from the negative side. So x equal to negative 0.1, negative 0.001, negative 0.001, what's going on with this one? And that will be x is 0, e is 1 over negative number. 1 over negative number is negative, e to a negative, not x is negative now. E to a negative number is a reciprocal 1 over something. So that's pretty small number. So 0 times a really small number. Assume this is a 0 already. So the 1 and 2, they're not exactly the same thing, but one of them apply L'Hopital, the other one we cannot apply L'Hopital. So let's calculate this example. All right, the first question. The first factor, limit of x, if x is approaching 0 from the positive side, it is 0. Okay. Now the limit of e to the 1 over x, if x is approaching 0 from the positive side. Occasionally I have students, they have some issue with this. So the way that we can do it is think about each component. The limit of 1 over x, the exponential part is when x approaches 0 from the positive side. It's 1 over a positive small number. This is a really big number. So this is actually infinity, positive infinity. So this limit is e to a positive infinity, because the exponent goes to infinity. So that's infinity itself. It's a really large number. But e to the 100 is really, really large. So e to the infinity is infinity. So we're looking at this is 0, this is infinity. So we're looking at a 0 times infinity case there. So how do we calculate this one using L'Hopital? And what our method is, if you have multiplication, we're not able to compare them relatively. So what we're going to do, we convert this into a division. So what we're going to do, how do we convert division? Like you see multiplication. Multiplication is the same thing as division of the reciprocal. So we write this into this. So it's going to be limit of e to the 1 over x. This is a complex one. I tend to change the easy one, the less complex one. There's 2 factors, this factor and this factor. The x factor is simpler, so I'm going to convert that one to reciprocal. So 1 over x. And then x goes to 0 from the positive side. Any questions so far? So you convert from a multiplication to a division, because almost all division can be written as multiplication, and almost all division can be reciprocal. It goes back and forth. So multiplying number is the same thing as division of the reciprocal. I mean, see, if you divide a fraction, it is equal to multiplying the reciprocal, right? So if you convert it back and forth, you realize the equivalent. And then we have division. If you have division, you can do L'Hopital, right? We're going to apply L'Hopital. We're going to find derivative numerator, derivative denominator, and then we see what's going on. So this is equal to apply L'Hopital. We have to differentiate the numerator. That will be differentiation of the exponential function. So you have e to the 1 over x. That's because the exponents, right? Exponential function. Then we multiply by what? Multiply by derivative of this, right? So what's the derivative of 1 over x?
Negative x minus 2.
Yes, negative x. Right, so it's negative 1 over x squared. Or negative x to the negative 2 power. So that's what it is. Also just the same thing, the denominator should be differentiated. Denominator is 1 over x, so the derivative is negative 1 over x squared. Okay, that's after the L'Hopital. And then we can cancel the common factor. These two cancel, right? Now this cancels, then you have limit of e to the, it become limit of e to the 1 over x. X is going to be 0 from the positive side. All right, for that we already did some premature calculation. That's the infinity. So now we already know that e to the 1 over x has a limit of infinity. So now that's our final conclusion. So for question number 1, the answer is infinity. Any questions? So this is really 0 times infinity, and our answer ended up being infinity because the infinity is in the exponential form, and the 0 is in the polynomial form. So the infinity actually have a higher order than the polynomial. Now, number 2, it's different. We have the limit is x goes to 0 from the negative side. So x is negative, but close to 0. So in that case, we still have the limit of x that is equal to 0. So if x goes to 0, then limit of x is 0 anyway. But then the limit of the other factor, e to the 1 over x, when x approach 0 from the negative side, it's going to be, I guess we have to look at the limit of 1 over x, limit of 1 over x, if x approach 0 from the negative side, it's negative infinity. So that's the difference between this one and that one. The positive 0, negative 0 causes different thing. So this is going to be e to the negative infinity. Right? Negative infinity. What is e to the negative infinity? It represents negative power means reciprocal. So it's really 1 over e to the infinity. And see, we know that e to the infinity have infinite limits. So this is really 1 over infinity. So what's 1 over infinity? Do you know? If the denominator is really, really large, 0. So this is 0. So it turns out these two factors, this approaches 0. The second factor also approaches 0. So what we're looking at is 0 times 0. So the overall limit is really 0. In this case, we don't have to apply L'Hopital. 0 times 0, which is still 0. What we will have some issue is 0 times infinity, because we don't know if it's really large or really small. If it's 0, then it's really small. If it's infinity, it's really large. We can multiply it. And we just have to prove which one has a bigger impact. But if it's 0 times 0, they're both approaching 0. So of course the overall fact is approaching 0. And that's the answer for the second question. And this is showing that for this function, around the 0, one side is approaching infinity, one side is approaching 0. Any questions? I think we can look at the graph to kind of see what's going on. So if we go y equal to x multiplied by e to the 1 over x, that's what's going on. So the function on the right side is approaching infinity, but on the left side it's approaching 0. So kind of verify what we have calculated is actually the truth. And we also have 3 and 4. 3 and 4 is different from 1 and 2. They are the infinity minus infinity case. So how do we solve this kind of question? Normally, what I think for most of the L'Hopital question is to convert it to a division. So that's the difficult part. Number 3, I see logarithm minus logarithm. That's according to the law of logarithm. You can convert that to the division. So we can convert division, and then we can do the calculation from there. The second one is what I'm concerned that if I have x squared minus e to the x. I remember how to convert that to a division.
Can we do the same thing? But use the reciprocal.
Use the reciprocal. Yeah, I think that might work. We'll see. So let's try to finish the first one. The first one, because the logarithm, according to the law of logarithm, logarithm A minus ln of B is equal to ln of A over B. So that's naturally created division, and then we can apply L'Hopital. So this calculation would equal to limit of x goes to infinity, logarithm, let's combine the two logarithm subtraction into one logarithm. So we have x plus 1 over x. Right? And then we see that ln is continuous, so the limit can be moved into the logarithm. So now we have ln of limit of x plus 1 over x, and then x approach infinity. And this is only true if the function itself is continuous. We move it in, and then that calculation we can do L'Hopital. Or you can just basically think about limit of x plus 1 over x. What was that limit? It's 1, yes. So at infinity, we're looking at the highest degree, highest power. X over x is 1. So this entire limit, the limit equal to 1. So the value is ln of 1, which is equal to, what's ln of 1? Special value.
0.
ln of 1 equal to 0. Okay, so that gave us the conclusion that it turns out at infinity, logarithm x plus 1 and logarithm x is pretty much the same. I mean, because the eventual limit equal to 0, so these two actually are pretty close at infinity. We can actually confirm that if you want to look at the graph of the whole thing that we just did. Ln of x plus 1 minus ln of x. This is how it looks like. And we're looking at what's behavior at infinity. When x is really 0, we can say they're almost 0, close to the y-axis now, close to the x-axis. So the limit is 0. The y value is 0 at far right side. Confirm this one. Then it's the last question. I've been thinking about how do I convert this into a division, and he said we can do a reciprocal. And so here, how do we convert this to a reciprocal? X is going to infinity. In my head, I would think about how large the quantity is. X squared is a polynomial. E to the x is an exponential function. If x is really, really large, think about 100. So x squared would be 100 squared. 100 squared. 10,000? 10,000. But e to the 100, just copy into the calculator, you can see that's a really large number. So understandably, this is a relatively small number minus a really, really large number. This large number, when x goes to infinity, is like infinity. So I think the answer should be negative infinity. If you have a smaller infinity minus a really large infinity, so the final answer should be a negative infinity. It's kind of like which one has a higher power thing. If this one has higher power, you would end up having a positive infinity. If this one has a higher power, you have a negative infinity. If they have relatively similar infinity like that one, you may end up getting 0 or a finite number possibly. So, but how do we theoretically prove this? I want to try to convert this into a fraction. We convert both of them to fraction, or convert one of them to a fraction.
Negative e to the x over x to the negative 2.
Negative what?
E to the x.
E to the x.
Over x to the negative 2.
No, there's still a subtraction relation. You still have to have that relation. It's not so.
What about a conjugate?
You may multiply the denominator and denominator by the conjugate. Normally when we multiply conjugate, our hope is that this two multiply to a simpler term. If we multiply this by the conjugate, it doesn't really simplify things.
Oh, yeah.
I see we're gonna, let me turn to this x e to x to the e to the negative x. See if that provides some insight. So we're gonna write x squared minus 1 over e to the negative x. So we write a 1 over the reciprocal. So that's the same thing as what we have there. So if you have a subtraction, one of them has a fraction, you will find a common factor. So the answer would be, this is equal to logarithm x squared e to the negative x over e to the negative x minus 1 over e to the negative x. Now we're creating fraction from the second term, and then we have a limit of e to the negative x is a common denominator. Numerator is x squared times e to the negative x minus 1. X goes to infinity. Okay, so after we change it to this form, what will happen is that numerator, the denominator actually approaches 0, because x goes to infinity. This is e to the negative infinity, so the limit is 0, and this is also the denominator approaches to 0. Numerator as what is the limit? So we want to confirm if they still L'Hopital. This e to the negative x, this x goes to infinity. This is 0. X squared is infinity. So that's infinity times 0.
So it's gonna, we have to do it again. And we'll get 2x. E to the x plus.
No, I think you remember what we have calculated over here. This is 0 times infinity, and then we end up having infinity because the exponential function has higher power than the polynomial. So in here we have x squared times e to the negative x. That is 0 times x goes to infinity. That's infinity times e times 0, right? X squared goes to infinity, e to the negative x goes to 0. But in this case, the exponential function still has a higher power than the polynomial function. So the 0 is going to have a bigger impact than the x squared. So this numerator has a limit 0. So 0 minus 1, the numerator actually has a limit of negative 1. And the denominator has a limit of 0. So it's negative 1 over. So the whole limit, the numerator actually approached to a negative 1, and denominator actually approached to 0. So that kind of confirmed the limit is negative infinity. That's what we originally assumed. But all these discussion is based on one single fact, that this must have a limit 0, right? And that we can actually calculate with a proof. So the foundation of all these calculations is based on two facts. Number one is that the limit of e to the negative x, if x goes to infinity, it's going to be e to the negative infinity, or it's going to be 1 over e to the infinity, which is equal to 0. 1, so the denominator approaches 0, one thing. Actually a positive 0, because the exponential function e to the number, it will never be negative anyway, so it's a positive 0. The denominator is positive, numerator is negative, that's what's making it negative. Another fact that we're applying is that the limit of x squared e to the negative x, this limit equal to 0, right? So 0 minus infinity over 0, that's negative 1 over 2, right? So how do we prove this? This is easier than this because for this you can convert this to a division. The e to the negative x is actually division by e to the x. So this you can confirm this by limit of x squared over e to the x goes to infinity. Then we can calculate derivative, and this is 2x. I guess I should write the limit sign. Limit of 2x over e to the x. But that's still infinity over infinity, so you're going to find derivative one more time. That's the limit of 2 over e to the x. Again, then x is supposed to go to infinity, right? E to the infinity is infinity, so this is 2 over 0. 2 over infinity, which approach 0, yes. So that's how we can prove that the limit of this part is 0. It's actually 2 over infinity. 0. So that kind of proof. I mean, we went a long way. I'm pretty sure the textbook might have a slightly different approach, but it worked. Question. So we try to use a little bit algebra or a little bit of the property of logarithm to confirm the one that does not have division into the one that has division. And here is multiplication. We also try to figure out a way to convert this into a division, because whenever you get a division and numerator and denominator both approach 0 or both approach infinity, you can always do L'Hopital. Any questions? That's case. Other question is set. All right. One more. The last group. Last group is what if we have exponents? The way we can deal with exponents is actually try to convert to a logarithm. So whenever you see an exponent, you were like, how do we deal with exponent? The inverse of the exponent is a logarithm. So like that. So suppose we have 0 to 0 power 1 to infinity or infinity to 0. The way we can calculate that thing is to take a logarithm of our function, and let's suppose the logarithm have a limit. So when you take a logarithm of the function, whatever exponential form is in the logarithm now become multiplication. So for that multiplication, you then convert it to a division, and then do L'Hopital to find this limit. So in this limit, you may have L'Hopital. And the rest of them, like so we're like finding the power already. So e to whatever that number you calculated, e to the L is your final limit for f of x. Any questions? So this is the thing we're going to convert it to a so we're really writing the f of x into a different form. So f of x equal to e to the ln. Now the ln of fx will convert any exponential form to a non-exponential form. That we can find a limit. The e, ln, they're inverse of each other. So f of x can be written as e to the ln of fx. So if this has a limit, and this entire f of x would have a limit of e to the l. And basically that's the fundamental way to handle this kind of scenario. Any questions? So we're gonna try to look at these two. These are a very classical scenario where we'll have to apply the trick that we were talking about in this section just to find its limits. All right, so with that, we're gonna do these two examples. All right, the first one, if you have x, we have x in the denominator, in the base, we have x in the power. So let's call this f of x. So what we're gonna do is, if you want to find limit of this function, and when x approaches infinity, 1 over the infinity, this is 0. So this is a 1 plus 0, right? This is a 1. Then the exponent is infinity. So this is one of those 1 to the infinity case. And that's how we know we need to apply L'Hopital. Over here is 0. x approaches 0, and the power x also approaches 0. So this is one of those 0 to the power 0 case. Among these two, this one is a really classical limit, and this limit, I can tell you, the limit equals e. You know the number e?
Oh.
The number e.
Yeah, that's how you find it.
Right, that's how you find the e. It's how, in some of the textbooks, we even go as far as define the e this way.
Yeah.
But how do we know it's e? And this is assuming we already have the e. But you can actually calculate it. They say make x equal to 2. So it's 1 over 1 over 2 to the power 2. That's 1.5 squared, which roughly is 2.25. The actual e is 2.72, so 2.25 is not too far from 2.75. But you can increase x out of just like larger numbers, like 1 plus 1 over 10 to the power 10. That will make it much closer. But if you want to find the actual e number using your basic calculator, you can do 1 over 10,000 to the power of 10,000. That's pretty much going to give you the e number already. So how do we find this limit? We know the limit is supposed to be e. This is how we calculate it. So according to our plan, we're going to convert it to this. We're going to turn this function into e to the ln. Note that e and ln are inverses. Right, they cancel. So we're going to actually pop this in here. You know e to the ln is inverse of each other. So now this is what we have. You can do this thing for any function, but of course we do it when we think it is helpful. But the same thing can be done for any function. So now let's convert it to this kind of limit calculation. According to what we know, that the e is a continuous function, so you can move the whole limit into the exponent part. So now we're looking at calculation of this. So calculate e to the limit of x goes to infinity, ln of the 1 plus 1 over x to the power x. So we're going to move the ln part, the limit, into the e. And then ln of the power can just go to the front. So now that becomes e to the limit of x times ln of 1 plus 1 over x. And x is going to infinity. So that's what we're looking at. Typically, now you have two multiplications. You get two factors, x times logarithm of log x. The logarithm part is bigger, so we tend to not to change anything. So we're going to change the x. It's going to go division 1 over x. We're going to multiply x and now become division 1 over x. So we're going to try to create a division for this, just to make this part a little easier to calculate. So this is equal to the limit of ln of 1 plus 1 over x over 1 over x. That's how we can convert this to a division. Question? So you see, if this whole thing equal to e, this entire limit must equal to 1. So all we have left is try to prove the green limit equal to 1. So what we're going to do is do L'Hopital now. We're going to prove the limit of the numerator. We're trying to find the limit of the numerator, which is 1 over 1 plus 1 over x, right? That's because the logarithm, 1 over the entire part is the logarithm, right? And then we still have to multiply derivative of the inside part. Derivative of the inside part is going to be negative 1 over x squared. That's the derivative of 1 over x. And derivative of the 1, we have 0 derivative. The denominator is also 1 over x. 1 over x has derivative negative 1 over x squared. Right? So you can see that this and this, they are the same thing, so they cancel. Here you apply chain rule, that's why we have that part. So now the same factor cancel, then you have 1 over 1 plus 1 over x. X is approaching infinity. So these factors, after we cancel out, all we're going to calculate is this part. And x goes to infinity, so 1 over x goes to 0. So the entire calculation is really 1 over 1 plus 0, and that equal to 1. So this entire numerator is equal to 1, so that's e to the 1. as our limit. It's this basically equal to 1 or equal to e. That kind of verifies the whole idea that this limit actually equal to e. And this is already applied in L'Hopital. In the application of the L'Hopital, we already think the limit of logarithm equal to 1 over x. And that proof has a e already in there. So the underlying logic, you already have the idea of the e definition in there. So it's kind of go back and forth. It's not the most fundamental way to prove that equal to e. So I like the original definition. I like to just plain define that as e rather than thinking of the limit equal to e. But everything goes around, even though it's a long run to prove this equal to e, but it works. So, any question? All right, do we have time? It's already 9:15. We'll finish the last one when we come back after the break. In the meantime, I hope you use your time during the break to finish your chapter 3 homework. Now we'll get ready. We'll review after we come back. That Thursday is a test 3, but I think we'll have time to prepare for it. I hope you have a nice break, and that will be it for today. Thank you.
Will you be available during the break?
You can always contact me. You want to ask question? You can contact me. We can set up a virtual meeting, or you can just call me, text me your question.
Yeah.
This is my number. Text me your question, or you can email me the entire question.